Okay, welcome to my presentations. I am Shahabuddin. Today I will discuss the paper recently published in Journal of Hydrology titled Climate Change and ENSO Significantly Enhances Seasonal Flood Occurrence in the Ganges-Brahmaputra River Basins. So the background is the GBM basin frequently experience the different seasonal flood like pre-monsoon, monsoon, and post-monsoons. Different floods have different impact. Like pre-monsoon always damage the agriculture crop like house and borrow rice, where post-monsoon also damage the agriculture crop like almond rice. On the other hand, monsoon flood is more severe impact. It poses the economical losses as well as severe threat to human life. So the seasonal hydrological dynamics have profound social impacts in the GBM basins. So in this basin, the climate change and ENSO impact is known for flood magnitude, I mean the annual peak flow. However, how they affect the seasonal floodings pattern is not revealed yet. For example, if the annual peak magnitude is influenced by La Nina ENSO, we say this La Nina similarly affect the other seasonal peak like pre-monsoon or monsoon. Similarly, if the climate change impact is higher or lower in the annual scale peak flow, can we say the other peak flow like in pre-monsoon or post-monsoon will be low or high? Here I highlighted recently published another papers that consider the annual scale peak flow and quantify the relative contributions of climate change and ENSO. These annual scale findings may be misleading if the impact of climate drivers vary across seasons. For example, if La Nina enhanced its flood peak in monsoon seasons, and another annual peak can be peak from if it is peak from post-monsoon or pre-monsoon. If the impact is very monsoon, pre-monsoon, or post-monsoon, because of these contaminations, the annual scale finding can be misleading. That's why the existing research found the low far value, positive far value means enhance the insurrex La Nina, but they found the relatively low far value. This can be contaminated by different diverse impact in among different seasons. So the object of research how climate change and ENSO phase affect the seasonal flooding patterns. Here is the proposed method. Here we use the large ensemble D4 PDF climate data continuing historical and non-warming simulation, and we use the CaMa-Flood for simulating the river discharge. After simulation, we define the flood using the 10-year return periods. Then we estimate the flood occurrence probability for each seasons and each experiment historic and non-warming. Then we use the fractional attribution risk framework to quantify the relative contributions of climate change and different phase of ENSO for monsoon, post-monsoon, and pre-monsoon seasons. And for mechanism analysis, existing suggests that if the upward wind motion is enhanced, it carries the moisture from down to upward and form the convective clouds. It's not only from the convective clouds, because of upward wind motions is enhance the vertical developments of clouds. After the vertical developments cloud is caused the severe rains. So we assume the mechanism will be like this. That's why we're using the vertical pressure velocity that indicate the wind motion either will be upward or downward. To investigate this, we use the regression method. Here the regression slope indicate either the Nina or La Nina enhance the upward or enhance the downward wind motions. Now the result. First, we check either the CaMa-Flood can reproduce the seasonal hydrodynamics in GBM basin or not. The existing found that the CaMa-Flood adequately reproduce the seasonal variation in the GBM basin. Then we further check the D4 PDF and CaMa-Flood can reproduce the seasonal variations in the GBM basin. Here we also found that D4 PDF and CaMa-Flood adequately capture the seasonal variability and seasonal peak value within the GBM basin. Here the blue line showed the maximum flow in 100-member D4 PDF, and the yellow one shows the minimum in 100-member. So the minimum and mass perfectly capture the observed black one. Now results. Here I showed the climate change impact across different season, pre-monsoon, monsoon, and post-monsoon. The climate change impact vary across seasons, not only season also across river. For example, in Ganges rivers in pre-monsoon season, far value relatively low, suggesting climate change impact relatively low, but it is severely high in monsoon and post-monsoon seasons. On the other hand, the far value for Brahmaputra rivers relatively high in pre-monsoon seasons and slightly low in monsoon and further low in post-monsoon season. Here I showed the relative contributions of climate change and ENSO impact across three seasons and three rivers. Climate change increases overall 40% flood occurrence chance across three rivers and three seasons, but the La Nina Nina impacts vary both seasons and rivers. For example, in Ganges rivers pre-monsoon seasons, La Nina enhance the flood occurrence risk positive far, but in monsoon season, La Nina enhance and Nina decrease. In post-monsoon season, again, La Nina enhance and Nina decrease. In case of Brahmaputra River, here we found relatively large par value in Inina. On the other hand, annual scale results suggest almost zero far value. This finding suggests that because of contamination, different peak from different season might be misleading the annual peak analysis. In case of Meghna rivers, we found the consistent findings like Inina enhanced in pre-monsoon, also in monsoon, and also post-monsoon seasons. Now, mechanisms. Here I showed the regression slope M. The black circle increase the La Nina increase the upward wind motions, and this the lower part of this basin blue color suggests Inina increase the upward wind motions. So after increase the upward wind motions, this mechanism maybe, and we found a relevant increase in precipitation in monsoon season. Like here, La Nina increased the monsoon perfectly match with these upward wind motion patterns, and here also Inina increase the precipitation lower basin, and here also the Inina increase the upward wind motions. Then we compare with the flood occurrence risk. Here I showed the correlation between the monsoon flood occurrence and ENSO. Here we also found like this blue area indicate the La Nina increase the flood occurrence risk, and the lower part like here and here Inina increase the flood occurrence risks. So it suggests that the vertical upward movement of wind velocity can capture the flood variation in these regions. Now the summary. Here we assess the climate change and ENSO impact on seasonal flood in GBM basins. Climate change increase overall 40% flood occurrence risk across different seasons and rivers, where La Nina Nina impacts vary by both seasons and rivers. Here we found El Nina rises in pre-monsoon season about 31% flood occurrence in Brahmaputra rivers, while existing research findings suggest almost no influence of ENSO. Here we found La Nina raises post-monsoon flood occurrence about 37% in the Ganges rivers. Moreover, the potential relationship between ENSO and seasonal flood occurrence in this area can be effectively interpreted by the vertical wind velocity, which serves as a large-scale control factor for flood variation. That's all from my side. Thanks for hearing.
Okay, thank you very much. So it's I think, very good application study using CaMa-Flood with large ensemble climate data. Okay, so I'd like to move to next presenter. Next talk is by Jayesh Parmar. Could you please share your screen?
I hope the screen is visible and I'm audible.
It's working, so please start.
Okay, so thank you. Good morning, good afternoon, and good evening, everyone. I'm Jayesh Parmar, PhD student from IIT Bombay. I'll be presenting the work titled Multi-Scenario Framework to Quantify Runoff-Driven Uncertainty in Global Flood Model-Based Hazard and Exposure Assessment over India. The work is published in Stoughton. So, going to the introduction, in line with the IPCC Directive and Sustainable Development Goals, flood risk is a tool for flood mitigation, planning, and management, encompassing the socio-economic impact of floods through hazard, exposure, and vulnerability component. So, the flood risk becomes a product of hazard, exposure, and vulnerability. While exposure and vulnerability assessment are feasible at large scale with humongous data availability, hazard assessment could be proceeded with the global flood models. And GFM like CaMa-Flood are highly dependent on graded runoff input. So the flood hazard estimates are only as reliable as the runoff inputs. So before going to the study, let's just understand how the large-scale flood hazard assessment is done in the literature. So briefly, there are two approaches followed. Approach one focuses on the signal to obtain the return period of the flood depth level, where the frequency analysis is applied to the long-term simulated flood depth time series. On the other hand, approach two focuses on the noise, where applying frequency analysis to the input runoff dataset is carried out for return period calculation of runoff, and thus the simulation of the flood depth is done, which might overlook the historical flow and realistic representation of hazard. In either way, the cascading uncertainty stemming from the runoff obtained from either land surface model or global hydrological models or runoff observations from the reanalysis, there would be uncertainty within the each stage of the hazard modeling. So our work proceeded with the approach one. Going to the motivation, just to understand, the intermodal flood depth variation was calculated in a previous work where variation in multiple runoff forced CaMa-Flood simulations showed the variation in the flood depth. And these flood depth variation are normalized. On the left plot is the shown for respective events for a small river basin within India, which is flood prone. And then this intermodal flood depth variation is compared with the population for the same event. And it is interesting to note that the variation is pronounced in densely populated regions, which might be impacting millions of people. And thus, we need a comprehensive analysis to have a plausible ranges of hazard and exposure based upon the runoff inputs. So our study addresses these gaps by explicitly accounting for runoff uncertainty introduced in the hazard assessment using a scenario-based framework derived from multiple global flood model simulation using CaMa-Flood. There are various data sets involved in this study, which are available in the paper, multiple runoff data sets, stream flow observation data for validation purposes, the flood extent validation, and for population exposure, the HRSL data was utilized. So going to the methodology, the study accounts for uncertainty through obtaining long-term time series of the flood depth using various runoff force simulation. Then these simulations are utilized to create a composite data set of conservative and optimistic scenario, where conservative scenario have a daily maximum flood depth among all simulation at a cell level at a daily time period. And optimistic scenario have the minimum flood depth, while the most efficient simulation obtained with the comparison of the river flow discharge is called as the best case scenario. And further, these composite data sets of flood depth time series are utilized for flood frequency analysis to obtain various return levels of flood depth. So initially, we calculated just to obtain which is the best case scenario simulation. We analyzed the NSE for a 30-year period simulation at a daily time step, where the NSE was calculated at a monthly scale. We found out that in general, most of the models or the runoff inputs works well for the region India, but the ERA5 reanalysis data comparatively performed well. We also calculated the relative error, which finds out that what extreme flows are efficiently simulated within the model. And again, the ERA5 reanalysis data showed much better performance, showing less relative error at most of the stations. So again, reiterating that each of the runoff inputs are designed for particular use, and we are not advocating that one of the data set is good, but again, the ERA performed comparatively well for Indian region. So this figure shows the composite flood depth time series for a flood event dated 22 August 2011. So we see that in the optimistic case, the flood depth is minimum. In the conservative case, we see that the flood depth is maximum obtained from the various simulation, and the best case is the ERF5 simulated CaMa-Flood outputs of the flood depth. So we applied the flood frequency analysis on the obtained flood depth time series, and we obtained the flood depth levels, which are then classified to the flood hazard levels based upon the significant impacts they produce on the normal functioning of the humans, or the impact on the buildings, or the damages they provide, which are based upon the Australian and the European agencies. So based upon the flood depth level, the hazard levels are defined for each scenario and respective return period depth. And again, overlapping the population dataset over this classified hazard maps give us the areas and the administrative units which might be at exposure, the population exposure varying within the different scenario can be given to administrative units for their understanding that what to be done about it. So, to conclude, the methodology and the result of this study provided a plausible range of hazard and population exposure at a 0.05 degree graded resolution, and an opportunity to build a GIS web-based visualization for dissemination of the information for efficient planning and management, such that in an economically constrained situation, optimistic scenario must be addressed for policy making, for intervention. And in economically abundant case, at least the best case should be addressed to have a efficient planning and management and for the flood mitigation. So this is the summary, and further work to improve the resolution and the inclusion of the human intervention like reservoir operation and again the levee operation would be incorporated for India region. That's it for today. Thank you to the CaMa-Flood developers, researchers around the world, and the open data agencies for providing the data and the model. Thank you.
Okay, thank you, JS, for presenting your work. Yeah, it's a very good assessment to understand the uncertainty in runoff data. Okay, so I'd like to move to next presentation. It's by Yuki Kimura, and he cannot join tonight. Oh, sorry. He cannot join today, so I'd like to share his recorded video.
Hello everyone, my name is Yuki Kimura. Today, I would like to introduce my paper. This title is as follows. Today's contents are as follows. As you know that, the demand for future climate risk assessment and future flood hazard map is increasing. In order to evaluate the impact of climate change, we face with many challenges. For example, impact assessment result based on an overwhelming number of future scenarios. Another challenge is that evaluating extreme events such as 1 in 100-year floods requires a large amount of climate projection data. However, standard climate CMIP6 alone do not provide a sufficient sample size. In other words, statistical uncertainty is a key issue. I would like to introduce previous research on statistical uncertainty. However, due to time constraint, I would like to introduce brief summary. Based on Hawkins and Sten 2009, from 2050 to the end of 21st century, differences among scenarios and models become the dominant source of uncertainty regarding climate change analysis. However, in the near future, up to around 2050, climate internal variability accounts for a large share of the uncertainty. It is well known that uncertainty from climate internal variability can be reduced by increasing the statistical sample size, for example through large ensembles. In this study, we focus on the hypothesis, can uncertainty be reduced by increasing the sample size by extracting data at the time of X degree warming across different future scenarios. The main objective of this study is to investigate whether uncertainty in future projections caused by the small number of ensemble members can be reasonably reduced. We propose the method to reduce uncertainty by merging multiple SSP-RCP scenarios and extracting the periods corresponding to the same warming level under each SSP-RCP scenarios. This slide shows the model analysis workflow and the dataset used. However, due to time constraint, I will skip the details today. If you are interested, Please refer to figure 1 in our paper. Our proposed method is based on one key hypothesis. The hypothesis is that flood hazard changes show similar spatial patterns across different SSP-RCP scenarios at the same warming level. To test this hypothesis, we examined how similar the geographic distribution of flood risk change is across multiple scenarios at the same temperature increase, for example at 2-degree warming. Specifically, we generated spatial maps of future flood risks for multiple scenarios. We then compared the spatial patterns and also used the heat map to quantitatively evaluate their similarity. In this research, we use river discharge as a flood hazard index, and we use change ratio of the 100-year return period flood discharge. The upper panel shows a spatial distribution of flood change ratios from the historical climate. The left panel shows 1.5-degree warming, while the three panels on the right show 2-degree warming under different SSP scenarios. At 2-degree warming, the spatial patterns are very similar across different scenarios. The lower panels compare the flood change ratios between different scenarios. The left plot compares 1.5-degree and 2-degree warming. The points are widely scattered from the 1-1 line, indicating different spatial patterns. In contrast, comparisons among different SSP scenarios at 2-degree warming show points tightly clustered along the 1-1 line, indicating very similar patterns. We also fitted regression lines to quantify this agreement. The slope for 1.5 versus 2-degree warming is 1.45, showing clear differences. By contrast, slopes among different SSP scenarios at 2-degree warming are 1.02 and 1.01, both close to 1.0. These results indicate that differences among different SSP scenarios at the same warming level are very small compared to differences between warming levels. Based on the confirmed hypothesis that flood risk changes show similar patterns across different SSP-RCP scenarios, we then examined how much our proposed method can reduce uncertainty caused by the small number of ensemble members. This slide shows the dataset and analysis framework. Specifically, we quantified the effect by comparing inter-GCM variability in project flood discharge changes at 2-degree warming from the historical climate between our integrated multi-SSP-RCP approach and SSP-5 RCP 8.5 alone. For future projection, there is no truth data like observations, so direct validation is difficult. However, reducing variability among multiple climate models is an appropriate indicator for evaluating the robustness of future projections. The upper left panel shows unbiased variance in the flood change ratio from the historical climate to 2-degree warming among 9 GCMs using our proposed method. The lower left panel shows the same variability using SSP-5 RCP 8.5 alone. Dark blue indicates larger variability, while light yellow indicates smaller variability. Additionally, the right panel shows the difference between the two approaches. Grids shown in red indicate areas where variability is reduced by our proposed method. From the right panel, we can see that unbiased variance among 9 GCM is reduced compared to using SSP-RCP 8.5 alone. Specifically, uncertainty in project flood risk changes is clearly reduced over about 70% of global land areas. Notable improvements are seen in high-risk regions, including major river basins in Europe, Asia, and Africa. These results indicate that the proposed method effectively offsets variability caused by random internal climate variability, including atmospheric chaos. Summary is as follows. Thank you very much for listening.
Okay, so this is the end of Kimura-san's talk. So if you have questions, maybe you can ask email to him. Or I'm a courser, so I can ask if you put question on chat. Okay, so I'd like to move to next talk. It's by Ifan Chen, and talk title is Impact of Tropical Cyclones and Socioeconomic Exposure on Flood Risk Distribution in Mekong Basin. So Ifan, could you please start your presentation?
Thank you, Professor Yamazaki. Can you see my screen?
Yes, I can see you, but please convert to the presentation mode.
Yes. Is it?
You need to swap displays.
Yeah, because I have two screens now. I think it's working now.
Oh, yes, it's working. Okay.
Yeah, thank you so much. Thank you, Professor Yamazaki. My name is Ifan Chen. I'm very honored to have the chance here to present our published in the year 2014 in Communications, Earth and Environment. So today I'm going to talk about the impact of tropical cyclones and socioeconomic exposure on flood risk distributions in the Mekong Basin in Southeast Asia. And as you know, tropical cyclone is disastrous natural hazards, and the tropical cyclone-induced precipitations is this an important factor in influencing significant floods. And actually, the distributions of tropical cyclone precipitation is of great spatial and temporal differences. From the distributions, we can see that in Western North Pacific, it has the highest amount of tropical cyclone-induced precipitation. And actually, tropical cyclone-induced precipitation, TCP, is closely related to It's related to the TC characteristics such as TC tracks. And from the late 1970s, there is a significant trend that we have observed in the Western North Pacific. There's a significant northward shift of tropical cyclone tracks, and we can see here. And it also has shown that it has significantly affected the regional precipitations, leading to decreasing tropical cyclone precipitation rate in the southern area of the basin, Pacific, and also increasing trend in the northern part of the Pacific. And the study area is Mekong River Basin, which is located in Southeast Asia, which is also under the influence of tropical cyclones from the Western North Pacific. And also this region is vulnerable to natural hazards such as tropical cyclones and floods because it has low flood protection standards, and also there are quite high population densities in this region. So in this study, we aim to investigate how does tropical cyclone activities interact with population exposures to flood risk under climate change. First of all, for this study, we first need to identify the tropical cyclone-induced precipitation. So here we employ a conventional method to extract the tropical cyclone-induced precipitation by using the 500-kilometer threshold. So here we can extract the tropical cyclone-induced precipitation within 500 kilometers of the tropical cyclone center, and then we extract all the tropical cyclone-induced precipitation over the tropical cyclone's lifetime, and also all the tropical cyclone tracks during our study period. So with this, we obtain the tropical cyclone-induced precipitation. Then we also obtain the non-tropical cyclone-induced precipitation by subtract the TCP from the total precipitation on daily scale. And then by that, we employ the VIC and CaMa-Flood model scheme, and then we force this model with two. So the other inputs are the same, but in these two simulations, the major difference is that in the first simulation, we use the daily precipitation as a forcing. then to force the Wick and CaMa-Flood model, so we can get the discharge and water levels induced from total precipitation. And then in the second simulation, we force the precipitation with the daily non-TC precipitation. So with that, we obtain the non-TCP induced discharge. And then the difference between total precipitation discharge and non-TCP discharge are considered as TCP-induced discharge. This is the main idea here. And also in this study, we simulate the historical tropical cyclone-induced the flood and also the future tropical cyclone-induced floods. And the future tropical cyclone track and climate data are obtained from the CIMIP-6, the latest CIMIP-6 high resolution map. And this high resolution map is aimed at increasing the simulation resolution in order to serve as a more reliable source for assessing climate risks, such as tropical cyclones. So it fits our goal of this study. And by doing this, we can compare the tropical cyclone-induced flood change in the history in the past 40 years, and also in the future, and see how does it change under climate change. And first of all, after this simulation, we evaluate the performance of this CaMa-Flood scheme, and we found that the model can simulate quite reliable river discharge and also water levels in the study area in the major hydrological basins. So based on that, we analyze the both historical and future tropical cyclone-induced precipitation TCP, and we found that TCP in the lower reach, like here, of the basin presents a decreasing trend in between 1967 to 2014, and then such in the future is also going to decrease, but in a lower magnitude. And then this such pattern of the trend of TCP is similar to the trend pattern of the tropical cyclone track the occurrence. Based on that, we also calculate the 25-year return period of tropical cyclone-induced inundation on great scale, and we found there's a significant spatial heterogeneity of the probability of tropical cyclone-induced inundation, and we can see that in the past, the tropical cyclone-induced inundation has increased mostly in the lower basin, especially like in Mekong Delta. But in the future, in the climate change scenario, this inundation, tropical cyclone-induced inundation risk will mostly occur in a lower rich basin, but there's a decreasing trend in the Mekong Delta. And this is the pattern we can see from the tropical cyclone-induced inundation from the hazard point. And then we construct a tropical cyclone, we construct the flood inundation risk index by combining both population exposure and the hazard. And then here we can see that the tropical cyclone inundation risk has a more complex spatial patterns than inundation. So it indicates the impact of changes in population exposure. And then looking at the relative changes in the past and in the future, we can also see there's a high risk area. It was here in the Mekong Delta, and it has been in the Mekong Delta, it has been decreased, but the lower eastern area remains the higher, the hotspot of the flood inundation risk region in the Mekong. And for here, we want to in order to support better flood management, usually it's implemented based on like administrative regions such as the sub-provincial region. So here we estimate the population, like how many percent of population exposure to the tropical cyclone induced inundation, and we summarize the on each province. We can see that mostly like in this moderate risk and also high risk both scenario, the areas facing the risk remains similar, like here in the Mekong Delta and the lower basin region, mainly Cambodia and also Vietnam. And we can see that in the future, under future climate warming scenario, there's increasing population exposure in this middle and lower eastern area of the basin. And for the high risk scenario, in the future, there's a general increasing trend in this region. So here, yeah. And so in general, tropical cyclone related flooding in this province with already high population exposure will continue to intensify under future climate warming scenario. So with this, our study highlights that both the tropical cyclone activity and human exposure has a role, plays important role in shaping the flood risk. And this is my presentation. Thank you for your listening.
Okay, thank you. I found very nice talk. And ideas, maybe the new tracer scheme can be used for your research. Must be
Thank you.
Okay, so let's move to next talk. Next one is by Urmin Begat, entitled Climate Change and Effectiveness of Dams in Flood Mitigation in India. So, Urmin, could you please start sharing your screen?
Hello, am I audible?
Yes. Slide is not the presentation mode. Yes, great. We can start.
Hello everyone, I am Urmin from IIT Gandhinagar. So I'll be presenting my paper, which is titled Effectiveness of Dams in Flood Mitigation in India under Warming Climate. Starting with the background, India is the third largest country in dam building after China and USA, and it has more than 6,000 plus large dams. And most of them were built between 1970 to 1990. And the major role of those dams was mainly irrigation and hydropower. But India has a vast network of dams which can attenuate flood during the high inflow days, and it can release later for the dry season period. So, but if we see the poor decisions in terms of dam can intensify flood in the downstream. And in the last year, in last to last year in 2023, there had been many cases where the dam stimulated floods in the downstream. So while dams play a crucial role in regulating river flows, but the uh, effectiveness is increasingly challenged under the climate change, and there remains a critical gap uh, to see the how the dams will affect the flooding in the downstream. So in this study, we addressed these two science questions. So how does the effectiveness of dams in reducing flood risk change under the future climate? And to what extent the upstream precipitation and antecedent reservoir storage affect the high flow variability in the dam downstream. So this is the model framework which we use. We combined 808 model land surface module with CaMa-Flood to route the stream flow and reservoir storage at each dams. So 808, we all know it is a land surface model which gives a gridded runoff at each grid, and this runoff can be routed through CaMa-Flood. So the climate data we use is precipitation and temperature from India Meteorological Department. And for the future projections, we use 5 members from CIMIP 6, which are performing better for India. And another a few data set which we used observe stream flow, reservoir live storage from government agencies, and the dams which were not monitored by government agencies, we took up the global reservoir storage data, which is a satellite derived monthly reservoir storage data for the remaining dams. So the model is calibrated against stream flow at more than 60 gauge stations. The triangle ones are the stations where model is calibrated against monthly flow, because these river basins are transboundary. The daily data set is classified, and the model was calibrated against 4 dams against the live reservoir storage data set. So the green dots are showing where the model is calibrated against the daily storage, which is available from the Government Agency of India. And the orange dots are showing where the model is calibrated against the monthly data set, which is satellite based. So the smaller reservoirs show lesser skills compared to the larger reservoirs, and it could be because of the those data sets are derived from satellite, and it could have some errors, mainly from the bathymetry estimates. So first, we tried looking at the historical events, where how the dams have impacted the flow in the downstream. So here we can see the dams have either mitigated or stimulated floods in the downstream. And even if we look closely, one dam also can mitigate flood in 1 year, and it can stimulate flood in another year. So first we looked at how historically in last 30 years dams have impacted the flood frequency in the downstream of the dams. So the left panel is showing the flood frequency in natural scenario without dam scenario. The middle panel is showing the flood frequency in the dam downstream and with dam scenario. So we can say that the median high flow frequency in the dam downstream have decreased from a median value of 35 to 13 per 30 years. And whenever this high flows in the dam downstream were observed, we looked at the antecedent storage 1 day before that event. And it shows that in most of the cases, the dams were full, nearly about 95% of the total storage. So after that, we looked at the linkage of the ability of dam to reduce the flow in downstream, with their correlation with the upstream rainfall and the antecedent storage in that dam. So here we see that the antecedent storage has a higher correlation with the ability of dam in reducing the high flows, and in the arid and temperate region, the correlation is as high as 0.9. So next, we looked at the influence of dams in reducing the future flood risk. So here we try to answer 2 questions. The first is, does the increasing warming increase the number of days when the dams are remaining full? And do the compound extreme of high inflow and high storage, which can trigger the flooding in the downstream, have become is going to become more frequent with higher warming levels. So talking about the first part, so here we see the change in the number of days when the dams are uh, remaining high storage, more than 90% of the capacity, compared to the reference period of 30 years, 1995 to 2014. And we look at 5 warming scenario, varying from 1 degree to 3 degree. And here we see that the uh, change in number of days is changing from a median value of 5 in 1 degree scenario to a median value of 15 which is showing a threefold increase in the number of days when the dams are remaining full in the future. And talking about the second question, where we look at the frequency of compound extreme of high inflow and high storage. So this frequency is also increasing by twofold in the 3-degree warming. And the frequency is going to increase from 0.5 events per year to almost 1 event per year in the 3-degree warming scenario. So the summary, we can say the performance of CaMa-Flood was evaluated at 60 plus gauge stations with and incorporating more than 175 Indian large dams, and the model performed well at all the stations with the scales more than 0.5, and it had the peak flow timing error within 2 days at most of the locations. And dams play a critical role in mitigating downstream flooding in India, but their effectiveness is strongly correlated with the antecedent storage levels. And under the warming climate, the inflow variability may intensify the flood in the downstream, but there is a need of better forecasting system. So this paper is published in NPJ Natural Hazards. Thank you everyone for your time.
Okay, thank you very much, Rumin. It's good to see how say CaMa-Flood with the reservoir impact assessment. Okay,
Thank you.
so I'd like to move to next presenter. Next one is by Jan Folkholz, and the title is Global Hydrological Models Continue to Overestimate River Discharge. Jan, could you please share your screen and start presentation?
Okay. Yeah, thank you. As the title says, global hydrological models continue. Let me. Sorry, 1 second. Global hydrological models continue to overestimate river discharge. This is a paper about validation of CaMa-Flood produced discharge. Here you can see this is the reference. And this work has been done in the context of the EasyMap project. The EasyMap stands for Intersectoral Impact Model Intercomparison Project. And EasyMap is essentially, it's a model intercomparison project for impact models. There's a whole bunch of sectors, and one of them is global water sector. And the idea is that that you can compare all results across sectors and models because all the models use the same climate input, they use the same socioeconomic input, and they have to abide to a simulation protocol which states this is the variable you have to deliver, this is the unit, and so on. And all the data is freely available. If you're interested in it, you can download all the results. And the paper idea was to feed the runoff that all the participating global hydrological models produce into CaMa-Flood, and the models were driven by observed climate. And at the time, there were 9 GHMs available, so you can see here which those were. And then these models also produce, if they can, their own discharge. And the idea was to look at to compare the discharge produced by CaMa-Flood with the discharge produced by the model internal routing scheme, and then compare this to GRDC station data. And this paper is a follow-up to a paper that was published in 2017. And just as they found essentially that CaMa-Flood at that time, in general, I mean, you cannot, it's not always true, but it reproduces the annual peak discharge better, both concerning amplitude and timing. But in this study, the results are less clear-cut, sometimes even a bit messy. So we looked at several metrics, and I picked 3 of them. One of them was we looked at the KGE performance index for the total timeline. So here you can see the models, so classic CWAM and so on. And the purple plot parts are the ones that are produced by CaMa, and the green ones are produced by the model internal routing scheme. And Jules actually used two internal routing schemes, or they used the internal routing scheme and DDM30. So this is what we call MIR2. And yeah, you can see that except for HydroPy, CaMa-Flood, like concerning the correlation. So here we see KGE. Here, and these are the three parts of KGE. So here you have correlation, bias ratio, and variability ratio. And concerning the correlation, except for HydroPy, for the total timeline, CaMa-Flood either performs better or equal to MIR. Here, for the bias ratio, most models produce too large of a discharge. So you can see one would be perfect, and most of the time we are above one. So that's the title. So I think this is one of the few results where you can really see like an easy to state result. And variability is rather mixed, with two models overestimating and the rest underestimating variability. And CaMa-Flood tends to go to larger values than the model internal routing scheme. So you can see here, usually from the green variability, when you go to the purple variability, you have an increase. You see this in most cases. And what I don't show here, we also looked at low flow meaning the 10th percentile. And this is also typically or mostly overestimated. Then we also looked at the annual maximum discharge. We have plots similar to this one, to the one I showed before, but here I picked a different plot. So what this does is you see again the GHMs on the left side, and then we take all the years, we do the median, and then like the observed median, and then we pick the years that were below this median, and we pick the years that are above, and then we look at what the model does, and then we see what is the share of years that overestimated. So here you can see that in general we see in low maximum flow and in high maximum flow we still see oftentimes overestimations. Yeah, except for instance, Mirok integrated land or classic. But yeah, so the same theme holds also for the annual maximum discharge. We see a lot of overestimation in discharge. And another feature we did is we looked at station properties. So I just show as an example the performance of the model versus the aridity index of a station, and aridity index is the ratio of precipitation versus potential evapotranspiration. And you can see the wetter a station is, the better the performance of the model becomes. So you see, like, it's not always true, but in general, dry station, you have like low correlations to high correlations, and in wetter stations, most of the correlations you find are pretty high. Just as a sneak peek, like one of the things we looked at is also station properties. In order to keep it short, I come to the conclusions. So we find that in general, models, both CaMa and the model internal routing scheme, are able to reproduce time series of daily and annual maximum discharge. We find that discharge is often overestimated. The bias ratio contributes most to reduced KGE performance numbers. Unlike in the previous version, CaMa-Flood does not show a general performance advantage, and since the previous studies has been done, 5 of the GHMs have added more important hydrological processes. Unlike the previous study, we found that, Fang Zhao, they found that CaMa-Flood reduces the annual maximum discharge, probably due to the floodplain, And we find the opposite except for one GHM. And yeah, as I said in this paper, you can find the reference online. We discuss many more metrics in detail. Thank you.